Hello everyone and welcome to your partner in education, Agile Rank Mate. Today, in this particular episode of VITEEE Workshop, we're going to be looking at some sample questions from the VITEEE exam, specifically in physics. Let's look at this set of questions, shall we? Here comes our first question. A straight line of mass 200 grams and length 1.5 meters carries a current of 2 amperes. It is suspended in mid-air by a uniform horizontal magnetic field B. The magnitude of B in Teslas is, we assume G equals 9.8 meters per second squared. Option A 2, option B 1.5, option C 0.55, option D 0.65. So, how do we solve this question? Well, we know that the mass is 200 grams. However, we tend to convert this into kilograms. So 200 grams would be equal to 0.2 kilograms. Length is 1.5 meters. Current is 2 amperes. Suspended in midair by uniform horizontal magnetic field, which is B. You need to assume or actually find out the magnitude of this particular B. Now, how do we do that? Well, this is where we use the formula for force acting on a current carrying wire by uniform magnetic field. And our particular scenario would look something like this. Straight line of 200 grams, 1.5 meters, 2 amperes current, and the magnetic field would be horizontal, uniform and horizontal magnetic field, which is B. Now, the force acting on current carrying wire in a uniform magnetic field, F, is equal to B times I times L times sine theta. Okay? Now, the first part of this particular equation is F, or force. The force acting on a current carrying wire. Now, if you look at the question says the wire is suspended in mid-air. Now, that means the weight of that particular wire or straight line is cancelled out by the force that the magnetic field exerts on the line. So basically, the force that is acted on in this magnetic field is actually equal to the weight of the straight line. And weight is mass times acceleration due to gravity. Hence, the provision to use G equals 9.8. Now, the right-hand side stays the same, BIL sine theta. All right? Now, we need to find the magnetic field, or B, the magnitude of that. So what we can do is we can shove the rest of the terms to one side and B to the other side. So B on the left side equals mg divided by IL sine theta. Now here's the next quirk. Remember that we have a straight line which is perpendicular to the uniform horizontal magnetic field B. And since it's perpendicular, that means the angle theta equals 90 degrees. Now since theta equals 90 degrees, sine of theta, which is sine of 90, equals 1. And IL times 1 would remain IL. So therefore, the equation boils down to mg over IL. Now we are going to solve for this particular equation. So B stays the same, mg over IL. Now we know that mass is 0.2. Acceleration due to gravity, we're told to take 9.8 meters per second squared over the current is 2 amperes and the length of the wire is 1.5 meters. Okay, now all from here on out, it's just simple arithmetic. 98 times 2 is 196. So 9.8 times 0.2 will give you 1.96. Divide that, 2 into 1.5 is 3. So all you have to do is 1.96 over 3, which you can't really do a long division, so you just do 196 over 300. 196 doesn't go into 300, so that's 0. At another point, you can get 6, which is 1800, and you get 160 left, which again doesn't go into 300, so you add another 0. So 300 goes into that 5 times, which is 1500, and then you have 100, which then goes 33333. So basically, the value of the magnitude of the magnetic field B is 0.65 Tesla. 0.65 Tesla is the final solution for this particular question. And guess what? From our options, it is clear that option D turns out to be the right option. 2 is incorrect because that's the current. 1.5 is the length of the straight line. 0.55 is also arithmetically not correct, because by doing all of the things that we did, we found out that 0.65 Teslas is the right answer. Moving on. This is the next question. We have a certain circuit. We need to find the value of I in amperes. So when they say I, which is this particular bit of current that passes through the middle portion of the given circuit. Now, in order to do this particular question, the way that it is told is you need to find out the net resistance, divide that with the given potential difference to find the net current, and then split it as per the arrangement of the resistors. So we're going to consider this particular parallel setup as resistors A and B. This resistor in series is C. This one over here is D, and the resistor that's next to the potential difference as E. Now, if you look at the figure, you can see that resistances A and B are parallel. Now, that means we're going to use the formula 1 over RAB is equal to 1 over RA plus 1 over RB. Now, basically, this means we'll have to do a whole lot of arithmetic, and the final formula that comes out of it, which is R of AB equals RA multiplied by RB divided by R of A plus R of B. We're going to use this straight away. Now, both of them are 4 ohms each, so it's 4 into 4 divided by 4 plus 4, which is 16 over 8, which is equal to 2 ohms. So resistance AB, this particular bit, is 2 ohms. Now, resistance AB, which we've just found out, is in series with resistance C. This one over here, that's 4 ohms. So the net resistance of those 3 resistors, which is RABC, is R of AB, which is the net of A and B, plus the resistance of C, since they're in series, which is 2 plus 4, that is 6 ohms. So far, so good. So now we know that across this particular section of wire, the resistance in total adds up to 6 ohms. Now we have another resistor in parallel that's connected between these 2 points. So we have another example of a parallel resistor. So RABC is in parallel with RD. Therefore, the total resistance ABCD is RABC multiplied by RD over RABC plus RD. That would be 6 into 4 divided by 6 plus 4, which is equal to 24 over 10, which is equal to 2.4 ohms. Now, finally, we have resistor E. Well, basically, we found out the total resistance between these 2 points as 2.4 ohms. Now, as the current passes through them and comes back here, it encounters E. So basically, this whole setup is in series with 1.6 ohms, that is resistor E. So we will mention that. So RABCD is in series with resistor E. So here we can find the total net resistance is RABCD plus RE, which is equal to 2.4 plus 1.6, which is equal to 4 ohms. So the net resistance is 4 ohms. Now we're going to use Ohm's law which says V equals IR, and we're going to convert that in order to find the current. So net current is V over net resistance, which in this case is 4 volts over 4 ohms. So here we have 4 ohms, the net potential difference is 4 volts. So 4 over 4 gives you 1, and its unit is in amperes. So the net current that we have is in amperes. All right, now, since we found the net current, we're going to use the theory that current passing through a parallel set of resistors is going to split off equally. Now, what does that mean? That means the I that is given in the figure, which passes through A, B, and C, is going to be calculated as the resistance of D, which is the other section that is parallel, over the total resistance, which is RD plus RABC, multiplied by the net current. So over here, RD is 4, RD plus RABC is 4 plus 6, which is 10, and INET is 1. So basically it is 4 by 10, which is 0.4 amperes. So the final value of I is option C, 0.4 amperes. The way we do it is we find the total resistance and using the total potential difference, find out the net current, and we split that net current between the 2 parallel sections of the circuit. And we find out the correct value of I, which is 0.4 amperes. Next question. When light of wavelength 300 nanometers falls on a photoelectric emitter, photoelectrons are liberated. For another emitter, light of wavelength 600 nanometers is sufficient for liberating photoelectrons. We need to find the ratio of the work function of the 2 emitters. Now, in case you don't know already, light with shorter wavelength has more energy. So that's how photoelectrons are emitted. So we need to find out the ratio of the work function of the 2 emitters. Now, what is work function? Now, work function mathematically is phi, and it is equal to hc over lambda. Now here h is Planck's constant, c is the speed of light, and lambda is the wavelength. Now h is a constant, c, the speed of light, is also a constant, which means that the only variable left here is the wavelength of the light that is, falling on the photoelectric emitter. So that means that the work function is inversely proportional to the wavelength of the light that's falling on it. So we're going to consider phi 1 is the work function of the light at 300 nanometers, and phi 2 is the same for 600 nanometers. Now phi 1 over phi 2 is basically 1 by lambda 1 over 1 by lambda 2, which is lambda 2 over lambda 1. Now lambda 2 is 600 nanometers, lambda 1 is 300 nanometers, which means that the ratio of the work function is option B, 2 is to 1. Basically, the first work function of the first emitter is twice the work function of the second emitter. And that's how option B turns out to be the right option. Option A is the inverse of that particular statement, which is incorrect. Option C and D says 4 is to 1 and 1 is to 4. This is in the case where there is a square. So for example, work function is proportional to square of wavelength or inverse square of wavelength, which is not true. So all of that makes option B, 2 is to 1, the right option. Now, let's look at the last question for the day, or for this episode. A monoatomic gas is suddenly compressed to 1/8 of its initial volume, adiabatically. The ratio of its final pressure to initial pressure is, and we're given the ratio of the specific heats of the given gas to be 5/3. Okay, so what does all of that mean? First of all, we need to know what process are we dealing with. The process is given as adiabatic. Now, what does adiabatic mean? It means that no heat is exchanged between the system and the surroundings, which means the system is pretty much insulated. Now, in an adiabatic process, when we express that mathematically, what it means is pressure times volume raised to specific heat is a constant. So basically P stands for pressure, V stands for volume, and this power here stands for the specific heat of the gas. Specific heat, the ratio of specific heats basically is the heat, the specific heat of the gas at both cases. So PV raised to nu is a constant in an adiabatic process. Now we're going to consider initial pressure as P1, final pressure as P2, initial volume is V1, final volume is V2 for the same gas in the particular adiabatic process. Okay, so since PV raised to nu is a constant, what this means is that P1 V1 raised to nu equals P2 V2 raised to nu for the two cases, initial pressure, initial volume, final volume. Now from here we can get the ratio P2 over P1 as V2 over V1, the whole raised to lambda. Now we know that the final volume is 1/8 of initial volume. So basically from the question we know that V2 is V1 by 8. And lambda, or specific heat, is 5/3. So we're going to substitute that. Just a minute. Unfortunately, I've made an error here. If you can guess, when we're doing the cross multiplication, P2 over P1, the other side is V1 over V2. So let's rectify that. So it's V1 over V2 raised to mu. Don't forget that, okay? So now we know that V2 is 1/8 of V1. We're going to substitute that. So basically V1 divided by 1/8 into V1, the whole raised to 5 over 3. Now, 1 by 1 over 8, V1 and V1 gets cancelled. 1 by 1 over 8 is 8. 8 to the power 5 over 3. So we can split that using the law of exponents. So basically a raised to m whole raised to n equals a raised to mn. So we're going to make it 8 to the power 1 by 3 whole to the power 5. Now 8 to the power 1 by 3 is the same thing as cube root of 8, which is 2. So basically what we get is 2 raised to 5, which is equal to 32. So option A, 32, turns out to be the right option. The other options are incorrect. So basically for an adiabatic process, this is what we need to remember. PV raised to nu is a constant, which means that we can compare it for initial case and final case when the monatomic gas is suddenly compressed. So because of that, we can use the volume and the specific heat in order to find the ratio of final pressure to initial pressure as 32. So option A, 32, is the right option. Now that concludes this particular episode of VITEEE Workshop. We hope you found this episode interesting. For more of our useful and interesting content, don't forget to subscribe to our channel, Agile Rank Mate. We have many videos of VITEEE and other examinations, so don't forget to check out our channel, and also don't forget to hit the bell icon below the video in order to receive the latest notifications. So until the next episode, take care, stay alert, bye-bye for now.